INSEE is a proud member of the Siam City Cement Group Public Limited, a leading cement manufacturer in Southeast Asia. The Siam City Cement Group provides world-class construction materials to a host of countries around the world. This includes Cambodia, Bangladesh, Vietnam, Thailand, Indonesia and Sri Lanka. With a plethora of landmarks and buildings that define the skylines of these countries, the Siam Cement Group pledges to be a role model in corporate governance and sustainable development. INSEE Cement, Sri Lanka's premier cement manufacturer, is the brand behind our country's leading cement products and the driving force behind making Sri Lanka more sustainable. With a reputation built on outstanding performance in the quality of our products, unparalleled customer service, the dedication of our employees, our respect for the communities in which we operate, and our ambition to set the standards for the industry of tomorrow, we have contributed to the growth of Sri Lanka with iconic developments across the island. Just to name a few: the Lotus Tower, Altair Residencies, the Colombo South Harbour, Southern Expressway, Mattala Airport, the Kalladi Bridge, the Kotalavala Defence University, Mahinda Rajapaksha International Cricket Stadium. INSEE has cemented its position as the most preferred local manufacturer of cement in Sri Lanka, with its widespread distribution network comprised of over 7,000 dealers in retail segment located island-wide. Today, we have 2 plants in Puttalam and Galle and 2 terminals in Galle and Colombo. INSEE's Sunstar brand is Sri Lanka's first cement product to be awarded the Green Labelling certification by the Green Building Council and was the first blended cement to launch in Sri Lanka. INSEE has a wide portfolio of cements and services to suit all your construction needs. The most popular among them, INSEE Sunstar, INSEE Mahavali Marine Plus, INSEE Extra for mass pouring concrete, INSEE Rapid Flow Plus, INSEE EcoCycle, INSEE Concrete, Conwood by INSEE, state-of-the-art innovation and development facility. Having been a part of Sri Lanka for almost a decade, we will continue to build on our long heritage of shared loyalty, creating trusting relationships with our business partners, people and community, and delivering our promise of building the nation.
In his career, he has done research on wastewater treatment in UASB reactor for his MSc and another research on seasonal changes in coastal erosion along the southeastern coast of Sri Lanka for his BSc Engineering. He was awarded Queensland University of Technology Postgraduate Research Award, Faculty of Built Environment and Engineering Top-Up Scholarship, Queensland University of Technology Higher Degree Tuition Award towards his PhD career at Queensland University of Technology. Dr. Daniel N. Subramaniam, sir, may I invite you to conduct your session.
All right. Thank you so much, Shaminda, for the introduction. Thank you so much, and thank you, Mr. Jan Koenig as well. So I will actually get into the presentation before I do the honors at the end of the session. So I'm actually an environmental engineer. So as Shaminda said, like I mostly did my researches on water related. And my PhD was in a stormwater management system, which is a bioretention basin. And that's how I got actually introduced to the porous concrete or the pervious concrete, because pervious concrete is also considered to be a part of the WSUD, the water sensitive urban design or low impact development, as it's called in the United States of America. Right, so I will just get into the presentation so I can speak. All right, so I'll just, I think Jan Koenig has actually touched on all of this sustainability, so I'll just run through before I get to the point, actually, the today's session on pervious concrete. So we speak about sustainability, and sustainability usually is spoken of in 3 contexts: the policy, the historical, so how we have developed so far, because we have been always developing from the days that we were hunter-gatherers. And then after that, we come to the knowledge context. So now whatever that you're going to discuss will be based on mostly knowledge context. And so these are the aspects of a modern society. So we have to manage all this stuff. We can't exist alone. We can't exist in isolation compared to, for say, about 4 or 5 centuries back. So we do have markets. So we have flow of materials, we have flow of energy. So, and then we have long distance and overseas trade. Then we have a financial economy. So we had to base all our improvement on that. And we actually felt it with this COVID-19 situation as well. So how we came to a standstill because of the economy coming to an end. And then the manufacturing processes, and we do rely a lot on the mining process as well, so resources, and the development of new technologies. And it's not only just developing new technology, we also should be able to share it with the community and the businesses and industry so that it can be implemented. So this is by definition, so I'm not going to dwell a lot in this. So the sustainability means that we have to think of our future generations, and they should be able to enjoy the environment as much as we enjoy. So that's principally the same. And when it comes to sustainability, then there are 3 pillars: economic, environmental, and social. So I will be mostly talking about environmental and the economic, but not even economic much. So we'll be talking a lot about environmental sustainability. And I could get this actually from the ISL Code of Ethics. So that actually, not only ISL, if you take even ICE or ASCE or wherever, that sustainability is actually intertwined into every code of ethics that is available for the engineering professionals. Right. So when it comes to environmental sustainability, there are 3 tools that are usually used, which is a life cycle analysis or life cycle cost analysis, then ecological footprint and planet Earth system. And out of this, we have common indicators. So usually they are calculated based on the ozone depletion potential, eutrophication potential, ozone acidification potential, and global warming potential, of which the global warming potential is mostly spoken about, which also depends on the carbon footprint. So we will talk a little bit about the carbon footprint of pervious concrete at the end of, but I will not be able to talk about the other 3 indicators in this session. Right. So about green materials, the reason why we actually should go for a green material is to reduce the impact on the environment. And usually it's a comparative analysis, because you can never make anything zero impact. So whatever that you do is going to have an impact on something. It could be a positive or negative impact, but it has to be some kind of an impact which is exerted on the environment. So what we actually go for is a comparative analysis, whether concrete is better than clay, the brick, or whether concrete is conventional concrete is better than recycled aggregate concrete. So something like that. And then the examples, so recycled materials obtained from sustainable sources or lower environmental impact material. And then construction material, are they actually green? So when it comes to, I think, I have been to many of the sessions of INSEE in the past, and every time they really emphasized on this one. And also most of the cement companies emphasize that cement is supposed to be the bigger pollution contributor to the construction industry. And so INSEE has also actually put forth a lot of hydraulic cements and all that, so which has a much less carbon footprint compared to an OPC, or ordinary Portland cement. So carbon footprint of a cement, and OPC would be somewhere around 1 to 1. So 1 kilogram of cement would have around 1 kilogram of carbon dioxide emission. So is pervious concrete a green material? So that is what actually we are going to look at it. Right. So as I said in the beginning, so water sensitive urban design or low impact development is a new concept that has emerged from, I think, the millennium. So around 2000 or 1900s, around that. And so what it aims to do is it focuses on the hydrology. Most of the time it focuses on the hydrology, and that if you're making a development, if you're undertaking a development, then the hydrology of the catchment should be made as close to what it was before the development. So to attain that, so whenever we do a development, we actually try to pave the surfaces more of the time. So pave the surfaces with impermeable pavement. So what we are trying to do is we are trying to make the paving surfaces permeable, so that, I mean, you can encourage a little bit of a recharge happening. So as you see in the picture, that is also a bioretention basin, which is a rainwater garden. So they call it the rain gardens as well. And a lot of the streets and pavements and car parks and all of them are made of pervious concrete. So we will actually get into that. So what is a pervious concrete? Yes, so in my definition, actually, I have almost 0% fine aggregates, as Mr. Jan Koenig said in his welcome speech, that yes, sometimes they actually put a little bit of a fines in there. That is to increase or they enhance the compressive strength most of the time, but that actually affects the permeability a little bit. So in most of the cases that we actually want to go for zero fines. So we don't use fines at all, no sand at all. So we just use cement, and then we have aggregates, we mix it with water, and we make the porous concrete or the pervious concrete. So the good thing about this is that you can customize this to any application that you want to do. So that is what actually we are going to look at today. So these are some typical, I'm just showing some of the texture of a pervious concrete. I think that is mostly made of about 5 to 10 millimeter aggregate size particles. And then we have some applications where we have some driveways and lawns, and then we have some parking spots and byways. And also one of the most interesting one that I have not seen much of an application even on the internet is the retaining walls. So usually we do a conventional concrete retaining, and then we have pipes, Eslon pipes just jutting out to drain the water. So I remember like one of my friends telling me, but I couldn't find it now, but in some places, even in the south, in Mathur area, people have actually opted to go for retaining wall using porous concrete, pervious concrete. But then we have to talk about the designs a bit when it comes to very high, tall pervious retaining walls. Right. So the primary intention, as I said, why this pervious concrete was developed is to actually increase the permeability. It is more of a hydrology related application, right? So to enhance the permeability, otherwise impermeable urban surfaces, then reduce flash flood frequency and volume, because I mean, if you have permeable surface, then you will reduce the flash floods. You will reduce the runoff, and that will reduce the flash floods. And then increase the recharge of groundwater. This is one of the most important things. If your groundwater is falling down, that is going to affect the stability also. And also is going to affect the water resources. So we need to have the groundwater, and we should not be altering the groundwater table a lot because of our development. And then the passage of draining fluids. Right now, so these are some of the other applications which have the potential of using pervious concrete. So actually, out of this, I think I have used about 2 in my research, which are still under analysis. So we can use them as a non-load bearing structural walls. I mean, you can design it in such a way that you can compromise on the strength a lot because it's non-load bearing, and you can increase the porosity, and so it becomes very light. That also can act like a thermal insulation, because the more cavities you have inside the porous concrete of the wall, that can act like thermal insulation. Also, they can act like a noise absorption walls. And so there are already a lot of research papers on the noise absorption on the road because of the rough surface. The noise that is actually emanating from the vehicle tire road movement is actually reduced a lot. So acoustics wise also it is better. And the thermal insulation, actually we have done research, so we have data, but I'm not going to discuss it today. But it shows some promise of that it can reduce the thermal insulation. So for example, you can use that as a partition wall, and you can have 2 different temperatures maintained at 2 different rooms at the same time. So you don't have to worry about the thermal heat transfer through them. Okay, so the general observations. So you can actually come up with a compressive strength varying all the way from 1 megapascal to about 120 megapascal. The flexural strength can be around 0.1 to 20 MPa. That all depends on your design. So we will be discussing a little bit on that. Then the porosity. The porosity is the most important factor in a pervious concrete, which can also vary between 5 and sometimes even I have got in research, sometimes you go all the way up to 45%. So that's a huge volume of pores inside that. And the wet density can change anywhere between 1,500 to 2,500, and permeability, you can have almost 0 if you are going to do a lot of compaction, and you can go even much higher than 2.5 meters per second. So that all depends on your design, how you're going to design it. So what are the challenges? Because as it was introduced in the welcome speech, pervious concrete has been used a lot in the developed countries. I mean, for roads they are using, for pavements, everything that I showed actually from abroad, nothing are from Sri Lanka. But so why is it not applied in Sri Lanka is one of the questions that I always ask. So it has a lot of potential, and it is limited in applications. So one of the biggest problem that I find is that the uniformity, because it's a porous structure. So every time you do a mix, and if you don't have a zero compaction or slump, then you're going to end up with a different arrangement of binder coated aggregates. You don't have fines, so you don't have a binder with like a fluid property. So usually in a conventional concrete, we speak the concrete as a fluid. To be precise, it's a Bingham plastic fluid. So you give some yield stress, and then after the yield stress, you have it's like a Newtonian fluid. So the problem with the pervious concrete is that is most of the time it has zero slump. So workability is zero. So that's one of the reasons why you don't see a very uniformity in the production. So if you're going to do industrial applications, you need to mass produce, and the mass production must be of uniform characteristics. If not, then it's going to have a problem. So that's one of the issues that we had in the applications. So as I said, zero slump, because the zero slump I'll be talking about with a picture later on. So we need to have a zero slump, or even probably around 10 to 15 millimeters of slump, not more than that. And then zero compaction, that is also, again, if you do a lot of compaction, then you are tending to block the passage of the water or the connected porosity at the bottom surface. So we need to have zero compaction almost. So most of the studies are actually with zero compaction, or a little bit of a tamping with the tamping rod. And then unable to define a general method to predict and design pervious concrete. Because as I showed in the previous slide, it varies so much. So we still do not have something like the design methods that we have for the conventional concrete. So, and then quantifying the porosity of concrete is still very uncertain. So I will be discussing a lot about this in the research, and require umpteen amounts of experiment prior to applications, because that we don't have a proper design system. So we need to have we need to do a lot of experiments before every application. Even every batch needs to be tested a lot, right? So that's because of that we also have a lot of wastages. So we can have a lot of wastages, and if the properties change a lot between two batches, then we have to waste them a lot. So that is another challenge that we have. So compaction of pervious concrete in the industrial application is uncertain, and most applications use admixture, which makes it more economically unfeasible, because most of the time in the developed country, they simply use the admixture. Even in the studies, if I note, most of the studies done in UK or USA or Australia or whatever, that they tend to use some admixtures. But in case if you're going to use it in Sri Lanka, and for example, for a loan or a payment system, we will not be able to use admixtures because it will be very costly. So we will not be able to bear the cost. Right. So regarding the uniformity and characteristics, so what is the challenge to mass produce with the uniform characteristics? So that I have already spoken about. So when you do the mass production, then every batch that you make must be consistent. So if you're going to vary the strength or the porosity of the concrete that you're going to do between batches, then you will not be able to use it for the same application. So you'll be wasting a lot. So the policy of zero slump and no compaction are to blame. And then the zero slump limits flow of concrete, which is required to avoid clogging of the bottom surface, the bottom face. So I think I have spoken about these ones. And yeah, and the other important thing is, because that we have a no compaction policy, the aggregates don't, and also the slump is zero, so it doesn't get rearranged. So the way you pour it, it'll stick. So it becomes, it's a very zero slump concrete. You can just think about that. So when you pour it into something, then it will be just sticking like that. So it's not going to move about or rearrange, so that, I mean, it becomes more uniform. So that is the actual cause for the uniformity. And it will be hard to attain same porosity of the same mix design due to zero slump and compaction. So this I have spoken a lot. And so even for same porosity, the porosity distribution may not be the same. Now, for example, we may have all the different mixes happening at the same time. And you may, even in your experiments, you might be able to get the same porosity, but you might have different compressive strength because the porosity distribution is not the same, right? So difference in porosity distribution will lead to variance in mechanical properties, including compressive and flexural strength. So expectation to predict, so what are we actually trying to do? So we have to be able to predict the performance of cast concrete based on design parameters. So before it actually goes into the application itself, we should be able to predict how it's going to perform, at least to some uncertain level. And so the uncertainty arises due to random errors or unaccounted extraneous factors. Now, for example, if you're considering some of the design factors as aggregate cement ratio, water cement ratio, and something like that, and all of a sudden climate might play an important role, which is not in your models. So that has to be actually rendered into the models that you're talking about. And then higher uncertainty leads to higher failure in prediction or higher prediction bounds. So in addition to challenges in attaining uniform characteristics, porosity distribution and its characteristics contribute to uncertainty that is less studied. I mean, most of the time, we will not be able to cast so many concrete samples. So concrete is already an uncertain material, because depending on the day that you cast, whether it's a rainy day or whether it's a dry day, whether it's the humidity is high, low, it's going to affect some concrete in some way, which is not going to be recorded and included in the models. So with that uncertainty, if you're going to talk about more uncertainty with less samples, then you're talking about the model predictions going way above the limited the levels. Okay, just when you look at this picture, you can see that we'll assume that all these have the same porosity. So when you compute the porosity, it's going to be the amount of the volume of pore divided by the total volume of the cube. So now, if you assume that all these pores have, all three cubes have same porosity, now the distribution is completely different. So there are two things that we can talk about. One is the spatial distribution. You can see in the first one, there is one pore in the middle. Then we have in the second one, we have 4 equal sized pores distributed, equally distributed probably in the cube. And then in the C, you have different sizes of pores, different spatial distributions. So like, now these are not going to be the same. They are not going to perform the same way as you would expect in the application. So most of the time, the studies have not actually taken this into consideration. So that's one of the properties that we would like to analyze. Right. So after this, the quantification of porosity. So I will be talking a lot about this later on. So we are actually talking about 5 porosities here, right? So which is a measured porosity, then calculated porosity, total porosity, effective porosity, and the connected porosity, which is going to contribute to the permeability. So measured porosity is the standard method where you dip the concrete into water and you measure the displacement of water, the volume of water that is displayed and displaced. And from that, you can find the amount of porosity. The calculated porosity is what I mean by that is to calculate the porosity volume of pores depending on the volume of constituents that we used. So we will know the mass of each constituent that we used, and we divide that by the density, we will get the volume of each constituent. And then from the total cube, if you deduct it, then you will get the volume of pores. Total porosity is actually, we are using the image analysis, which I will explain later. And effective porosity is devoid the boundary effect that we have on the top and the bottom, because when we are casting in the laboratory, we cast in the molds, and the molds have a rigid surface, and the rigid surface is going to induce some kind of a boundary effect. So we will talk about that later today. And the connected porosity is something that we still couldn't find out, because we are measuring the permeability separately, but we will not be able to talk about the connected porosity because it's a 3-dimensional effect. Okay, so which of these actually correlates to mechanical properties? So does the distribution affect compressive strength or flexural strength relationship? Right. So if you look at this picture, the pores A and F, so they are actually in the middle of the cube. They are not exposed to any sides. So now if you dip this concrete cube into the water is not going to enter any of these A of F, right? The water will enter through B, C, E, and D, but it's not going to enter A and F. So what will happen is when you do the computation of porosity, A and F will be considered as solids. So this is, so the measured porosity that you're going to do by experiment is going to be an underestimation of actual porosity. The second one, if you take the part D and E, yes, they will be exposed to the surface, so they will be included in the measured porosity. But compared to B and C, D and E is not going to contribute to permeability because it doesn't let the water transfer. So it will let the water enter, but it's not going to transfer water. So it has to be B and C, but even C is not going to contribute to permeability because it's in the cross-sectional side. It's going to be in a vertical side to the fluid flow that we are going to consider. So only one type of pore is going to actually contribute to permeability. So how are we going to do that, right? And then after that, so this is also something that we found out in our researches, is that there is a boundary effect. So if you take the total porosity, it say, for example, it's going to be about 0.3. But what we found out is the 0.3, the major fraction of the pores are actually in the sides, in the boundaries. So what you have in the middle is a little bit significantly less, say something around 0.2. So that we call the effective porosity, and the other one we call the porosity in the boundary layers, right? And then when we talk about permeability, so in the previous picture, I said that it's going to be the same through the, if the pore is actually connected from the top to the bottom, then it will contribute to permeability. But the problem is the permeability as a number does not depend only on the connection. It also depends on the size of the pore, right? So because of the capillary effect and surface tension, everything is going to play an important part. So it's not a linear relationship between the size of the pore and the permeability. So we should be able to develop some kind of so we do understand, because permeability is a big question even in unsaturated soil mechanics. So we don't usually teach that in school, in the university, and also sometimes we more or less tend to use it as a constant. Right? But then actual factor is that you should be able to model it with probability distribution functions, right? Okay, and then the important one, this is something that I actually came across in the recent past, which I found very interesting in some of the research papers, that they're talking about this ITZ, interfacial transition zone. So if you take an aggregate coated by cement or the binder, then there is a layer in between the two, which is called the ITZ. And that affects the mechanical properties of the concrete a lot. So most of the time we do the microstructural analysis for this. And what I found interesting is that the absence of fines in the pervious concrete is actually an added advantage in the ITZ analysis. But I'm not very sure, because I mean, not many researchers are available, because I think we are also trying to do something in the future. So it actually alters the ITZ. So the thickness of the ITZ, how much is contributing to the mechanical properties, because also they found that most of the time the crack is propagating through the ITZ. So our application should be focusing more on enhancing the ITZ than what we have in the matrix as in the rest of the binder, right? So the current research avenues, what we find currently in the contemporary literature, is actually looking at most of the time some kind of a relationship models. Empirical, most of the time is empirical models. So porosity versus compressive strength, and aggregate size versus porosity and compressive strength. Then gap grading of aggregates, rather than just using one size of aggregates, you can use, say, for example, 5 to 10 and 20 to 25, something like that, so that you can mix and you can try to get. And the inclusion of waste fillers like fly ash or rice ash. Then you have something like the coir is used. Sometimes the coconut shell husks are used. So there are a lot of other things in the waste kind of a thing. And then there are fibers used inside the pervious concrete. And then use of admixtures. So I, as a person, do not actually suggest use of admixtures because of the cost effect that we have in Sri Lanka. And then the other basic researchers are in the usual experimental cubes as samples. But the problem that we have is that they use very, very small number of samples. So it doesn't actually attend to the uncertainty that is already affecting the findings. And one of the tools that they're using is the CT scans and X-ray methodologies and stuff like that. And they are very costly. So to take one picture itself, you have to spend a lot of money. So you will not be able to cast about 6 repetitive samples and take 6 pictures, because that's going to incur a cost. So most of this time, these analyses are a little bit different. So as I said, they are using mercury positometry, X-rays, CT scans. The other problem that we found with this image analysis is that to convert the image to a binary or tertiary system itself involves a lot of algorithms, and the algorithms has a lot of issues with uncertainty, because then you are playing with the uncertainty a lot. You are either compromising on overestimating or underestimating a pore. You will not be able to get the correct pore sizes because of the color codes and stuff like that. So we thought, and we actually have used imaging technology using the normal cameras that we have for the digital cameras, but we had to do a little bit of preparation before the samples. Okay, so what are the limitations that we have in generalizing the studies that we have? So as I said, so people have actually done a lot of studies on developing models between the porosity and compressive strength. But the problem is, as I explained before, just one porosity is not going to dictate the compressive strength, because the porosity distribution is another factor. Pore size is another factor. Pore shapes are different factors. So now all that has to be tendered in. But so what we have at the moment now is there is a lot of uncertainty around that. So one study will have another model, which will not be used by another study, because depending on the sizes of aggregates they used, depending on the characteristic of aggregates, the aggregate shape, aggregate size, distributions. So now that's one of the things that is making the generalization of models very challenging, and lack of analysis and understanding on the propagation of uncertainty, because as I said, uncertainty propagation is very important in researchers, and also for a proper application of in the industry, and unaware of the pore characteristics that mostly contribute to the uncertainty in data and model predictions, and usage of high-tech, high-cost imaging techniques, which are actually not helping, rather than just having a big system in place. And then we have vulnerability in lack of understanding on image analysis techniques, as I explained, algorithms dependent and transformation and analysis of images. Then lack of focus on durability. This is one of the things that was I noticed in the current literature, is that the durability is very seldom analyzed in porous concrete. That's probably because that we are still in the early stages of doing research in pervious concrete. So most probably once we are done with that, we should be able to get into the durability. But as Mr. Jan Koenig said, so actually the pervious concrete is quite durable. So we don't have to really worry about that, but it also depends on your design. And then seldom studied on an industrial application. So this is something that I would really like to do, to apply it on somewhere and see like how it performs in the natural scales. Right. So those are actually in the current context that we used. So this is a little bit about what our research is. So we have actually focused on these 7 things. In the last, I have done research on pervious concrete for the last around 8 years. So I think ever since 2014, I have been involved in pervious concrete, but I have not done much of publication. The reason is I want to collect ample data before I start doing the analysis. So now that I have got the data, so these are some of the experiments I have already done. So I have looked at reducing the uncertainty mainly by design parameter optimization. I don't want to get into these admixtures and things like that. So one of the tools that I used is using the proper aggregate size and also and a degree of compaction that can induce some kind of a uniformity in pervious concrete without compromising the permeability itself. And then we analyze the pore characteristics, porosity characteristics, and optimize design parameters such that uncertainty is reduced in tandem, including usage of filler materials. Then we have used a lot of different analytical tools, including we are using some machine learning methods as well to develop robust mathematical models to predict and consider various applications. So I'm not actually looking just at the pervious concrete as a pavement structure. I'm also looking at non-load bearing structural walls, where I'm also talking about the heat transfer and the sound penetration through those. So I'm doing some analysis on that as well. And then we are actually talking about the boundary layer and durability as well. So I'm not going to discuss all of this today because much of this data is not yet analyzed. So we are still analyzing, and I will be discussing a few things which are immediately applicable to the industry, and that we have already actually done some publication and which are still under publication. So important one. So this is what I have been talking about earlier. Slump has to be 0. So here you can see the trend. So it is actually going from, if you look at this plot, so here the slump is 0. And then after that, the slump is increasing exponentially. And I have shown in this one, the 2 different things. So the slump of the 0.35 water cement ratio and the bottom phase. Now, I have not applied any compaction to these ones. These are with 0 compaction. So we only had some tamping on the top surface. And you can see that the bottom surface is completely filled. So it doesn't actually contribute to permeability. So no matter how much you design, it's not going to act as a permeable concrete. So you can see now this slump at 0.35 is only about 40 millimeters. So the 40 millimeter is actually causing this much of a trouble. So that is one of the reasons why in the research also they have proposed that the slump has to be maintained almost 0. So when the slump is 0, then you can think about the flowing conditions of pervious concrete. And this is about the porosity analysis I was talking about. So I have already explained to you the, so I'll go one by one so that you will get some idea. So this is the method that I was talking about of measured porosity, so experimental way. So you find the height of the water, water level, and then you dip the concrete in, and then you take the difference of the water level. And so that is going to give you the volume of water displaced. So that will be the volume of solids in the concrete. So you had to deduct it from the total volume, and then you will find the porosity. So this is measured porosity. So this is the image analysis that I was talking about. So you can see here, so we cast cubes in here. We cast the cubes, and then we, and then we take the core samples. So each core sample is 100 millimeter diameter. And then we actually spray paint with the black color, and then we hand paint it, the cut surface. So you have a distinction between the pores and the solid surface of this, the curved surface of the core. And then we take a panoramic view of the digital image. We use usually, sometimes we use phone cameras, iPhone cameras, or sometimes now we are using actually the Sony A7 III, the digital camera, which are economical cameras. And then we actually convert them to the binary. So we don't have a big algorithm for this because it's already in black and white almost. So it's very distinctive. So we don't have to, so we reduce the uncertainty a lot in this case. And then we do the cropping and we do the binary imaging, and then we calculate the area of black versus area of total. So the black ones are the aggregates, and which will be actually giving us so not aggregates, sorry, the solid surface. So that will give us, the rest will give us the pore. So I think the black is the pore and the white is the solid surface. So from there you can calculate the total porosity. So these are some of the observations we found, that there could be a lot of uncertainty. You can see here, there is some uncertainty on this part here, and then we have some there as well. So there are a lot of uncertainty as well, and which cannot be explained, so which are inexplicable. So that's one of the reasons why we wanted to go for a more robust method in analyzing. Right. So now this one, so what we did is we took the cube, the picture that you saw, and we split them into 10 strips like this, horizontally. And we found the porosity of each strips. So that is with depth. So the picture that you see here is actually the 10 strips, that the porosity of 10 strips with depth. So on the x-axis you have depth, and on the y-axis you have porosity. So you can see there's a significantly higher porosity in the top and the bottom layer. So you can find here and also at the end. So now this is the one I was talking about. But if you look at the middle layers, they're almost constant, but they vary with the aggregate to cement ratio, which is another one, aggregate to cement ratio, and also it varies with compaction. But for a particular given sample, then they are most probably constant. So this is something that we call the effective porosity, the application of effective porosity. Okay, so now this one is giving us the relationship between actual porosity and effective porosity. So you can see the uncertainty is much less. So we have reduced it so much so that we can depend more on the study, on developing the models. Okay, and then after that, the next one that we really need to identify in pervious concrete compared to the conventional concrete is the aggregate packing. Because in a conventional concrete, if you take, so every other space, the pore space will be filled by the binder, the matrix, the fine aggregates and the binder. So you're definitely going to have some kind of a support in all directions. But if you take porous concrete or the pervious concrete, it is very skeleton. So the skeleton must be depending on the aggregate packing, right? So any kind of particle packing. Now, in this case, we can talk about binder coated aggregates. So each sphere can be considered as binder coated aggregates. So now when you talk about aggregate packing, if you are going to pack the aggregates in an optimum way, so you can, beyond that, you will not be able to packing. So for example, in the materials, we would have learned that atomic packings. So you have BCC, the body centered or the face centered, HCP, OCP, and there are so many other things. There's a simple cube. So now beyond that point, you will not be able to pack it further. So that pores will be actually remaining free. Now, for an aggregate, a pervious concrete or a conventional concrete, to have an optimum aggregate to cement ratio, when all the aggregates are packed in optimal way, then the binder should be able to occupy all the spaces in between. So based on that concept, we should be able to have an optimum AZ ratio for either of, for any pervious concrete. So what happens is, if you have an aggregate to cement ratio less than the optimum AC ratio, then when you are compacting, what is going to happen is the aggregate particles will move closer to each other. So what it will do is it will squeeze the binder out of the path that it's going to move. And if your aggregate to cement ratio is lower than the optimum, then you will have more cement or more binder in the cube. So what will eventually happen is the excess binder will be evicted from the cube. So even though you use an aggregate to cement ratio, so for example, about 1, if you do the compaction, you will end up with something, the optimum aggregate to cement ratio. So you will never be able to keep all that inside, right? But on the other hand, if you use aggregate to cement ratio, which is more than the optimum, then no matter how much you compact, you are not going to get zero. I think, yeah. So you're not going to get to zero porosity, right? So that is something that a concept that we developed. Now when it comes to aggregate packing, you will also have a lot of impact. Now we assume all this of BCC, FCC, and all that, considering that it's going to be spherical particles. But in the general sense, it's not. They are not spherical. They are very, very shapy. So, for example, flaky, elongated, and angular particles. So they are not going to be the same packing as you would expect, like you put some marbles into a jar. So that is something is going to give. So when monosize. So what we did is we did some analysis of putting all the aggregates into a mold without cement or water. We found that the porosity is about 44, right? So, but whereas you would assume, if you take body centered, you would assume a porosity of 38%. But here we found actually 44%, which is almost, I think, like a lot like a simple cubic structure, right? But that is due to the shape and other factors of other characteristics of aggregate. So we are not going to get in there and discuss about that. So the aggregate shapes and size distribution are actually well defined in geotechnics. So we use the parameters a lot in geotechnics. So in our experiment, in the aggregates that we used, the porosity is about 44 plus or minus 1.2. So based on that, we calculated the optimum AZ ratio to be 2.36 for our studies. So anything more than 2.36, you will never be able to get zero slump. Anything less than 2.36, no matter how much you put more, with compaction, it's going to come out. Okay, now we'll go into our data. So this is actually giving us the data that we obtained. So the x-axis has the number of blows, that is a compaction. So we actually compacted our samples based with the standard proctorama, which is 2.5 kilograms and dropped from a height of 300 millimeters. And so this is actually giving how many blows we gave, right? 10, 15, 25, 30. So how many blows actually we are given to the, when we are casting the cube. And on the y-axis, you have the porosity. And each color is actually giving us the aggregate to cement ratios. So you can find here, with the lower aggregate cement ratio, you can do a lot of packing actually. You can do a compaction. They are compactable, sorry. And then as we move up the aggregate to cement ratio, we can see that the compactability is actually reduced. And the turning point is happening somewhere between around 4. Aggregate to cement ratio 4, whereas you would expect that to happen at 2.36 theoretically derived value. If you look at this one, so this is actually giving the same graph with the blows and aggregate to cement ratio, but the y-axis is giving us the compressive strength. So with lower aggregate to cement ratios, you can give a lot of compaction and your compressive strength exponentially increases, whereas any aggregate to cement ratio above 4 or above 3.5 is not actually producing any significant change in the compressive strength. So we actually find out that the optimum is not happening somewhere in 2.36, but it is happening in somewhere around between 3.5 and 4. Because one of the reasons is you can see here that no matter how much compaction we do, we will not be able to get anything less than 0.1 porosity, right? So for the mixture that we have, no matter how many blows that we give, we will not be able to get more than less than 0.1 porosity. So that's one of the reasons it's actually contributing to a higher optimum AZ ratio. So this is actually showing us the fraction of actual porosity and computed porosity. So that's the fraction that we're talking about. Here also you can see that a distinct pattern is there between 3.5 and 4 AZ ratio. So therefore, we actually come up with an ideology that somewhere the optimum is happening. So no matter how much you put less than 4 is not going to help you with the pervious concrete. So actually this is again showing the apparent, the measured porosity and actual porosity. And you can see beyond 4, it's stabilized, a lot stabilized. But before 4, there is a big difference. So what we did is we did the, okay, I think I have, yeah. So porosity could never reach 0%. And aggregate size distribution and aggregate shape affect the packing of aggregates and the matrix of the skeleton of pervious concrete. So the aggregates do not necessarily come into contact with each other. Now, what our exact concept would be like 2 aggregates, when you give compaction, they will move with each other and they will come in contact with each other. But in pervious concrete, in actual situation, it doesn't happen. So they will have a resultant thickness of binder in between them. So because of that, we will not be able to get to that 2.36 optimum AC ratio. So then after that, what we did is we did another further analysis on image. So this time what we did is we actually marked the aggregates alone, and we left the binder also out. So binder is also now considered into the white area. So what we can do is we can do the same analysis with comparing with the previous analysis. So you get the binder thickness as well. So binder, aggregate, pores are now 3 separated. And when we did that, we found out that for higher AC ratios of 2.5 or 3 or whatever, and when we did the compaction, it actually assumed it became around 4. So you can see that with compaction, it actually comes to somewhere around 4. Right? So you can see everything. So after that, I mean, beyond 4, it's going to increase anyways, because the binder will not exit the surface, right? So now this is, I think, one of the important things that we found out, because there's no point doing anything less than 4 AC ratio, and you're not going to get the permeability also. So when we did the adjustment, we found that they are all somewhere around 4. So they actually come to now apparent versus actual porosity. Earlier we had a bit of a less in the lower AC ratios, but then we found out that everything comes into the 95% confidence. 95% confidence interval within that interval itself, right? And then we have optimization of compressive strength. So compressive strength can be optimized using aggregate characteristics, AZ ratio, water cement ratio, and compaction. So water cement ratio, we are going to keep 0.3. It is almost universally accepted. And then small aggregates lead to higher strength. You can go up to, we actually got up to about 25 megapascal without any compaction at all. Right, so small aggregates in the way that I mean, about 2.36 to 5 or 8 millimeter particles. Now you may wonder whether it has permeability. Yes, they do have a permeability much more than about 0.5 meters per second. So that is more than enough. So that can be done. And then gap grading of aggregates can enhance up to 35 to 40 megapascal without any problem. Right, so that gap grading means, as I said, you take 2 different aggregate sizes and you mix proportionately, right? So this has to be done as a design. So this is another model that can predict the pervious concrete, the porosity and compressive strength. So this can be actually depicted by a mathematical equation this way, right? But so you can see the 95, the very good fit as well, and you should be able to predict the outcome as well before any mixing. So this is another model that is also available to predict the compressive strength based on the porosity, which is a widely used model for porous material. Now, for example, powder technology. So Rice-Quich equation is actually applied for powder. And also it is applied for porous concrete in some studies. So that's why we went for this, and we found out that they also satisfactorily predict. Okay, now I think the one before last is the boundary layer effect. So as I said before, when you have the boundary layer, so how much does the boundary layer affect, right? Because if the boundary layer, we found out, now you can see one side, now this is the bottom boundary, and the bottom boundary can go up to say around 20 millimeters. So now 20 millimeters is almost now in one layer. And if you have both layers together, so out of 150 millimeters, about 50 millimeters gone in the boundary layer. So this is not acceptable in many cases. So when we are doing the laboratory study, we should be mindful about this boundary layer impact. But then one important factor that we noticed is also the compaction. Now, I did not talk about the compaction in the earlier ones. Now, compaction also supposed to be around 30 blows of compaction with a standard Proctor rammer is actually giving a uniform property. So you can attain a little bit of more uniform porous concrete mixture with 30 blows of compaction, and it doesn't reduce the porosity either. So here also you can see the 15 blows is actually having a huge variation in the boundary layer, right? The thickness of boundary layer with the different AZ ratios. But if you take anything other than that, 30, 45, 70, 60, 75 blows are all giving almost constant boundary layer thickness. And that is almost less than 10 millimeters for all of them. So this actually shows that a compaction of 30 blows is going to yield us more uniform production of pervious concrete rather than not having any compaction. So this is actually showing the variation of how it is changing with the blows. So 30 or 45 somewhere in between, and then after that you see stagnant level. Right. So this is for the top boundary. So what we discussed earlier was the bottom boundary layer. Now this is about the top boundary layer. The top is actually not having any impact because of the rigid surface, because there is no surface on the top. So this is actually the effect of how we pack. So when we are actually closing the cubes, what we actually do is we just put some more and then we try to flatten it. So that is the effect. So we can definitely see that it is not varying with compaction or aggregate to cement ratio. Nothing actually affects it, and that is about 5 millimeters on the top. So which is actually important in I think the industrial application, because in industrial application, bottom layer is a little bit not of concern, because anyway, unless you are going to put it on a compacted soil layer, if you're going to put it over an unbound layer, then it's not going to affect much. The boundary layer will be actually reduced because it's not a rigid surface. But the top one will be actually, because depending on the industrial application, the top boundary layer needs to be accounted for in industrial application. Okay, now the last section that I want to discuss today is the filler addition. So we are adding, in this one, we are adding fly ash, and you can see how the slump varies. So now when you're adding the fly ash also, you have to be very careful about how much the slump that you're going to go for, because in any case, we should be able to keep the slump somewhere close to zero, so that, I mean, it doesn't affect the permeability or the porosity of the pervious concrete. And this is actually showing you the strength that we can get with different water cement ratios. And so we can, I think for the conventional also, we have used most of the time is about 10% of substitution. Now, one thing that I would like to note here is that for all the other studies that we used in the previous ones, we used hydraulic cement. So conventional cement and hydraulic cement doesn't actually have a lot of impact in strength when it comes to pervious concrete, because we are talking about the lower range of application, the strength. So it doesn't actually have any impact at all. But for this study, we used the OPC because we are substituting with the fly ash. So probably in the future, we should be able to do it with the hydraulic cement as well. So, and this one, so instead of having just one ash, we thought of adding fly ash and ricer's ash together in, so that the total substitution is 10%. So we don't want to go more than 10% of substitution. So we keep that as a 10% substitution as a benchmark. And we try to put the two different ashes so that, I mean, whether we can get a higher strength. And we found out that we could attain about 20 to 21 megapascal with 10% RHA. Now, again, another point to note is that these don't have any compaction at all. So we have not done any compaction on this concrete that we have done the filler addition. So these are all attained without any compaction, with very high permeability. So there is a lot of room to increase this strength even more. And also we can, without compromising the permeability. But for this one, we use the aggregate to cement, aggregate sizes as around 8 to 12 millimeters. But in the other studies that we showed before, we used aggregate sizes from 12 to 25 megapascal. 25 millimeters. So those are very huge aggregates. Right. And on the right, we have the cost of using them. So we can see that using of 10% of ricer's cash is going to give us the lowest. So we can actually find out to the economy that we're actually looking for. So this is actually showing the compressive strength. For the F is indicating the fly ash, and then the other one is indicating, the R is indicating the ricer's cash. So this is actually showing you the compressive strength. Again, so no compaction in this study as well. So you can see that ricer's cash addition is actually helping a lot with the enhancement of the compressive strength. So this is actually the cost for example, we thought for a particular design, say for example, M5, M10, M20, M30, If you're using different concrete, so for example, with conventional concrete, pervious concrete with 40 blows, pervious concrete with 30 blows, pervious with fly ash addition of 10%. So this is the analysis we have, cost, right? So we can definitely see. So the cost is much higher for conventional, and we do have very less cost for the other one, significantly less, right? Especially when we are going to the higher grade concretes. And also when we look at the carbon footprint, we also can see that the conventional concrete is unduly actually spending so much of a footprint, imparting a bigger footprint than that you can do with the pervious concrete or the alternatives that we have. So these are some of the things that I want to show. And so the research in progress, as I said before, so we have all these data that we are analyzing, and we are trying to develop a model that could predict the performance of the concrete entirely with the design parameters. So we have considered a few parameters, but we aim to include more parameters so that, I mean, it can be a robust model. So that's probably soon we will be able to make it. And then we also have durability analysis. We want to do the publications as well on the durability and the thermal and sound properties of pervious concrete. And definitely one of the important things that I really look for is the uncertainty. So I would like to, at least, even if you can reduce the uncertainty, I would like to define the uncertainty in the models so that, I mean, anyone user who is going to use it would be able to understand the improbable fractions of their application in the models. Right, so that's all I just want to say. Thank you so much, and I would like to thank the INSEE team, Mr. Jan Kunik and Dr. Musa and Mr. Adhikari, for giving me this opportunity actually to share this, whatever that we are doing, you know, on a greater platform with all the practitioners. So thank you so much, and also I would like to acknowledge the members of our pervious concrete research group that we have. So these are the members. We have staff members from different walks of life, actually, not only just civil. We have people from computer mechanical, and also we have a lot of students, research assistants also part of that. So I would like to thank on behalf of them as well for giving us the opportunity to portray this one. Thank you so much.
Thank you very much, Dr. Daniel Subramaniam. Application potential of pervious concrete and analysis. Thank you again for the fruitful session, very fruitful session, and I'm sure that there are questions to raise and further clarify the points. May I invite our Isuru Samaranayaka, Assistant Manager, Quality Assurance, INSEE Concrete Collaboration Space, to conduct the Q&A session. Isuru, over to you to conduct the Q&A session.
Thank you, Dishan. Good evening, ladies and gentlemen. So, thank you again, Dr. Daniel, for the superb and very informative presentation. So let me bring you a few questions which are raised by our participants. So the first question is, what is the preferred aggregate size or grading for the pervious concrete?
Okay, so as I said before, so I have used aggregate sizes from 2.36 to 25 millimeters. So that's the variation that I did. So depending on the application that you're looking for. So for example, if you want a very high permeable concrete layer with less strength, probably you should go to the high end. So for example, from say 18 to 25 or 12 to 25 millimeters. If you're looking for paving with more robust structure on skid resistant and all that, probably it's better to stay somewhere between 5 to 10 millimeters. So it actually depends on the application that you really sought. Yeah.
Okay. Thank you, sir. So the next question is it possible to use reinforcement in pervious concrete?
Okay, so that is one question that everyone asks about pervious concrete. So what I did is, okay, we cast one concrete with reinforcement, I think in 2017, and we just put it out in the environment to get wet and everything. So it actually still functions well. But then if you're going to use corrosive material for reinforcement, then probably that is not a solution for a load bearing application. So we had to go for either stainless steel or something like that that doesn't corrode. So because it is anyway exposed, so the pores are going to expose the reinforcement to the environment. So it will have water flowing through, it will have air going in. So it might have bacterial growth in there. So it could be anything. So definitely that's going to have an effect. So yeah, it has to be actually thought of in the design phase itself.
Okay. So there's another question. Pervious concrete affects on durability in terms of chemical attack. What are the available precautions?
Okay, at the moment, as I said, so something that we have not actually done, and it's not very available in the research as well. So this is an avenue that we need to actually think about, because most of the time we speak about the porous paving and things like that. So I think some studies are done in sulfur attack, but they have not come up with a conclusion as yet. So that is something that we need to explore. Yes.
So the discussion is on what are the compaction method used or finishing methods when applying industrially.
Okay, in the industry, mostly they use the roller compaction. But so what we found is in the research, the literature also they say, so the Marshall compaction is a little bit of a good value or a good relationship or a good metaphor for the compaction that we use in the industry, the roller compaction or even impact compaction. So you would use impact or roller most of the time. So, or maybe just a vehicle just going on top of that. So that is something very similar to what we use in the landfill compaction as well. So that for that kind of a compaction, so it is quite understandable from the Marshall compaction or the Marshall or the standard Proctor, which we are actually using. So that's one of the reasons why you're using. But we have done some analysis on vibrator compaction, because vibrator compaction is a little bit different. Because it acts on the basis of concrete behaving like a fluid. So that is a concept. So vibrator, for the vibrator compaction to be very effective, the concrete must be very fluid. But porous concrete is not so much of a fluid property. So this vibrator thing might have an impact on the segregation also in this thing. And also in the researchers, they have found that vibrator compacting is not quite a metaphor for industrial compaction when it comes to roller or otherwise. But I think I'll be studying that quite often, very soon, on how this vibrator is going to change, because how much vibration you are going to give and on what level you are going to give. Because all will be now, for that to analyze, we have to actually look at the rheology of the concrete. So yeah, that's the answer for that.
Thank you. So as a last question, what are the relevant standards available in terms of compressive strength, workability when it comes to the pervious concrete?
Okay, as I said, for the design standards, there are none. So we still don't have any standards as such that you would find for the conventional concrete or the structural elements that you would go for, the European standard or whatever. For these ones, actually, they don't have anything available as such. So they are in the process of making. So most of the time, actually, depending on the application that you are going to apply this for, you have to base your design based on the experiments that you're going to do. So we are actually trying to. So that's one of the reasons why I actually discussed about these models, because we are in the process of actually making making a model. So we actually halfway through when it comes to the model prediction, but the code has to be developed. Yes.
I have another question. So I was fascinated to hear that and this can be used for vertical members as well. I mean, can we go for a little higher members, like 1 meter height or something like that?
What members? Sorry, I was not very
clear. Vertical members like walls.
Yes. Okay. So in the beginning, I spoke about retaining walls. Now, when it comes to retaining walls, like it all depends on the flexural. So you can get a very high flexural strength in this one as well. But I have not seen a very good application on this porous concrete. Maybe you might need to have some kind of a reinforcement for that to actually happen. But I'm not actually sure about that as yet. So I think we have to actually work on the vertical members. So,
If I can just add something, Dr. Daniel,
Yes.
that in Latin America, for example, Latin America, tropical countries, they use a lot of what we call no-fines concrete. This is what you explained today, the porous concrete or pervious concrete for retaining walls. Therefore, you can like reduce the hydrostatic pressure, and as you said, the flexural strength is okay, and therefore that is really for them a very good solution for water management, air slide. Therefore, it is successfully used in a lot of countries like Ecuador, like Costa Rica. It's tropical countries, you know, and I think for Sri Lanka, this is a very good avenue of research, as you said, and very often I would say that it's not about the technology as it is, because you said it very well, you master very well the mix design, where are the key parameters, but when it comes to scale up to industry, very often is about contractor having the right tools, the right, equipment to be able to handle such a product. This is true for any new concrete type that come to the market. If I talk tomorrow, self-compacting concrete will be the same. You should take a special precaution for formwork, you know. And I think that yes, for vertical, it is really used a lot. Okay, for somehow water management in somehow for this application. Yes, probably I can share with you some experience from Latin America we had, and it is quite interesting. Thank you.
Yeah, thank you, Dr. Musa. Yeah, I would really like to have a chat with you because yes, I have not seen this retaining wall here, but it has been applied in other places. But I really wonder why. I mean, we cannot use, because we can get very high flexural strength in this concrete as well. I mean, nothing less compared to conventional concrete. So it all depends on the design, as you said. Yeah, thank you.
And also depend on the I say the hydrostatic pressure. You know, I mean, how much you want to release pressure, what is the water management system, you know, it's all, you don't need to have a very, very high porosity. You know what I mean? That is the point here. Therefore, you can somehow play with the density of such a concrete to have the right connectivity without having very big pores, you know, where you can lose also some mechanical somehow engineering property. Yes, sure.
Yes.
Okay.
Okay, so with that, I think we have answered almost all of the questions and a lot of information were shared. So thank you very much again, Dr. Daniel, for the nice presentation and all the details shared with us. So over to you, Disha, for the next.
Thank you very much, Isuru. Isuru is our assistant manager for quality assurance in C Concrete and I2I collaboration space. Thank you again for conducting the quality assurance Q&A session. Let me invite Dr. Mosa Balbaki, Head of Products and Solutions Portfolio in C Cement, to conduct the vote of thanks, to give away the vote of thanks. Dr. Mosa, may I invite you to give away the vote of thanks?
Yes, thank you, Dishan. I mean, first of all, I would like really to thank everyone who has attended this very interesting session on knowledge sharing on this pervious concrete. As I said, every time, you know, we are used to meet physically here at Palliagoda to our innovation to industry collaboration space. But at least the virtual part is still a solution for us, and we are very happy to have such a high number of participants, over 150 every time, to this session. Thank you so much for your participation. Having said that, I really would like to express my gratitude for this outstanding presentation. You know, pervious concrete, yes, it could be new in somehow in Sri Lanka, but it has been used a lot in a lot of countries for different applications. I'm not going to name them. And I would like that to say that Dr. Daniel, you have done an excellent presentation. I would say that, you know, people who are interested a lot about concrete technology, they can see a lot of similarity when it comes to importance of aggregate, importance of the transition zone, importance of all these parameters you have mentioned. And this was a very interesting somehow presentation to gain somehow I say a new avenue, okay, for our industry, for our construction industry, develop solution. And when you started, I mean, you have talked a lot about the sustainability part, you know, and you know, we are under huge pressure all around the planet to have to limit our not on footprint in terms of CO2, but to develop what we call really the nature-based solution. Because if you know, it's not about CO2 only. You know, the CO2 is not anymore like when we talk about climate change. We are not in the climate change, we are in the climate problem already. It's not the change happened already, you know. But we have to be very careful with the nature. It's about the diversity, the biodiversity, about water assessment, water management. As this pervious concrete is used a lot, you know, in several countries to better manage in cities where you have high density, you know, the flow of water that you can reduce, for example, downstream, some flooding, you know, it has a very good somehow solution. And when it comes to, I say, business in circularity, you know, we can integrate even construction demolition waste to this type of concrete to make it even better in terms of sustainability. Therefore, thank you so much. It was very interesting. We lost contact since almost a year and a half. This was not by purpose, really. I could never come and visit you at your university in Jaffna. And I hope soon we can have this contact with Adhikari. Just 3 weeks back, we planned to make a tour in Jaffna, but finally it was kind of like postponed for the reason we know very well. And hopefully the country will go more to a better, let's say, control of this pandemic. I hope it's so much. Therefore, I also somehow would like to, I say, to thank the entire team. You know, this is like when we talk in terms of knowledge sharing session webinar online, this is a 15th consecutive one we do. That is really, there is a big team, a very motivated team behind organizing this type of knowledge sharing session. I would like to thank really my entire colleague from INSEE, from I2I, to give this support and somehow manage very well to continuously somehow have this knowledge sharing session the last Thursday of each month. Therefore, I will not take more time. Thank you so much, Dr. Daniel. I hope soon we can meet again, we can connect again, and we can work together again. I hope so much. And again, thank you so much for all the participants. It is always really very, I would say, grateful to have you with such a high number every time. We see such a high number that you are really committed, and it shows clearly the capability, the motivation of our engineers, of our all the stakeholders in this construction industry in Sri Lanka, that we want really to somehow lift up the standards. We want to learn, we want to implement fast, and that is quite interesting. And this is indeed the main objective of this knowledge sharing session, is not to sell cement, to make any promotion, not at all. We just want to share knowledge, and thank you so much. Therefore, hope we will see you again, all of you, the next month, the last Thursday of next month. And from now on, I would like to wish you a nice evening. You stay safe with your friend, your family, your neighborhood, or everybody. And thank you so much. Okay, goodbye.
Thank you.
Thank you very much. Stay safe.
Dr. Mosa. Dr. Mosa Balabi is our head of products and solution portfolio in Cement. Thank you again, Dr. Daniel Subramaniam, Senior Lecturer, Department of Civil Engineering, University of Jaffna, for conducting the 14th webinar session and the 29th knowledge sharing session organized by the INSEE I2I, Innovation to Industry Collaboration Space. So until we meet you again with the 30th knowledge sharing session, which is the 15th webinar session, be safe. Good night.
Okay. Bye-bye.
Thank you. Stay safe.
Bye-bye. Thank you so much. Bye-bye.